All right, and can everybody see my iPad screen okay? Yes, okay, excellent. Okay, and you're gonna see at the top here, it says exam 3 material. So again, anything we go over today is not going to be for Wednesday's exam, it'll be for the following exam. All right, sorry about that. All right, so first off, we're gonna start off with a review problem, and this is a Q equals MCAT problem. So here it says how much energy in joules is needed to raise the temperature of 150 grams of water from 21 degrees Celsius to 95 degrees Celsius. So this is similar to things that we've done in the past. So we want to know about energy or heat. That is our Q. So we will be filling into this formula right here. Q is what we're looking for. Again, that's your energy or your heat. Your mass is 150.0 grams. Anybody remember what our specific heat is, C for water? I see 1, and 1 is in calories, but we do need it in joules. So that is correct, but for calories. Anybody know it in joules? So this is a value you're going to need to know by Wednesday. So specific heat of water in joules, there we go, 4.184. All right, so make sure you know this value right here by Wednesday. And then we have our change in temperature. And I hear questions about tutoring, so what I have is that time after we finish lab. So between the time we finish lab and 9:45, I am here and I'm happy to help you guys if you want to go over anything. So that's kind of my tutoring / office hours time. But if you can't make that time, talk to me, but I think that's probably the best time. All right, so our change in temperature, we went from 21 to 95. So we have 95 degrees Celsius minus 21 degrees Celsius. So again, our change in temperature is always final minus initial. And then I hear questions about whether this particular PowerPoint slide will be on Wednesday's exam. So this one that we're doing right now, this is a review, and we did do similar things to what we're doing right now before spring break. So this type of a question is fair game just because we already covered it and this is a review. But as we move forward, then that's all new stuff. All right, go ahead and take a minute and calculate Q. Let me grab my calculator. And let's see. So I see a question that says T2 minus T1, and I think that's about our temperature. So change in temperature is T final minus T initial. And since here we went from 21 to 95, that's how we get that 95 degrees Celsius as the final, 21 degrees Celsius as initial. All right, so anybody find the value for Q? Anybody brave enough to type it in? All right, so I'm seeing 4.6 times 10 to the 4th from a few of you. And this is in the unit of joules. Excellent, so several of you are getting this. Excellent. Any questions on finding this value, or anybody want to go over how we calculated this or go into more detail about how we plugged into this equation? Okay, So again, this is a review slide. So now let's go ahead and get to some brand new stuff. And here we're going to look at what we call a heating curve. So it says how much heat is required to turn 2.50 grams of ice at -5 degrees Celsius into water vapor at 110 degrees Celsius. So the reason that this one is different than what we've seen before is because here we have to do some phase changes. We're starting out with a solid ice, and we're going to end up with water vapor, which is in the gas form. So the heating curves are when you're changing both the temperature and the state. And the state is whether you're a solid, a liquid, or a gas. So before we do the problem, I want to draw kind of a picture so we get an idea of what we're doing. So I'm going to draw a graph for us. And on the left, we're going to do our temperature. We're going to do it in degrees Celsius. And on the bottom, on our x-axis, I'm going to put energy. All right, and this is going to be for our problem. So in our problem, we started at -5 degrees Celsius. So I'm going to start down here somewhere, and I'm going to call this -5 degrees Celsius. All right, so as we apply energy to our ice at -5 degrees Celsius, the temperature is going to start to go up. But something strange is going to happen at 0 degrees Celsius. Now, if we didn't have to do any phase changes, what would happen is it would just keep going up like this. But we do have to do a phase change. And what happens when we do a phase change is all your energy goes into that phase change. So it starts looking flat here. And what's going on in this flat area is melting. So right here we're melting. Our solid is becoming liquid. So when you have ice at 0 degrees Celsius and you put in energy, instead of it getting to a hotter temperature, what's happening is all that energy is going into the melting process, that solid becoming liquid. And once upon a time, we used a different word for that. We called it fusion. And fusion is another word for melting. So any questions so far about what's going on here? When we're at -5 degrees Celsius and we apply energy, the first thing that's going to happen is our ice is going to get warmer. But once it hits 0, that is its melting point. So now all our energy goes into melting, and we don't increase the temperature until everything has melted. So any questions about anything there? All right, so now we're going to assume that we have melted everything. We have liquid water. So if you have liquid water at 0 degrees Celsius and you start applying energy, the temperature is going to rise. And it's going to keep rising till we get to 100 degrees Celsius. So here we have liquid water. And let me go ahead and label this over here. This was ice. Okay. So liquid water, temperature starts rising from 0 up to 100. But then at 100 degrees, we're going to have another one of these plateaus. And that's because we have another phase change happening. So here we have what we call vaporization, also known as boiling. So during vaporization, our liquid is becoming a gas. So just like with the melting, once you hit 100 degrees Celsius, we cannot increase our temperature until we have vaporized everything, because liquid water cannot go over 100 degrees Celsius. We can only go over 100 degrees Celsius when we're in the gas phase, but everything converts to gas before anything can raise its temperature. So here, we are vaporizing, we're boiling, we're turning everything into gas. Once everything is in the gas form, then we can start raising our temperature again. And in our problem, we are going to keep heating until we get to this 110 degrees Celsius. So this is called a heating curve. And I know it doesn't actually have any curves in it, except for maybe some of my bad drawing if I didn't do a straight line. But our heating curve shows us first, we go up diagonally on the graph as we change our temperature. Then we plateau whenever we have a change in phase. Then we go up diagonally again, plateau, and go up diagonally again. So let me go over that in more detail, and I'm going to go ahead and number these, and I'm going to say 1, 2, 3, 4, and 5, like so. All right, so I'm going to start off with number 1, and I hope I didn't make it too small. I know some of you are looking at your cell phones here. So in step 1, we are heating the ice. So here the temperature is changing. And in fact, it's increasing. And what we're going to see is anytime the temperature is changing, we're going to use Q equals MC, oops, got my M, MC delta T. So this delta T is because your temperature is changing. Now in step 2, we can't use that anymore because we don't have any change in our temperature. So here we have no change in temperature. So instead what we're going to do is we're going to use delta H of fusion, also known as delta H fuss. All right, so whenever we're doing a phase change, we're going to use our delta H, our enthalpy values, rather than using Q equals MC delta T. And the reason is, if we were to try to use this formula, but delta T equals 0 because we're not actually changing our temperature, we would get Q equals M times C times 0, and anything times 0 is 0, so you would just end up with a 0 here. So if you try to use Q equals MCAT where it doesn't belong, you're just going to get the answer of 0 because there's no change in temperature. Actually, instead of doing that, I'm going to go ahead and... So instead of erasing it, I'm just going to go ahead and do that. All right. Questions on anything that we've talked about so far about how we're going to handle number 1, where we're heating the ice, and number 2, where we're melting our ice? Oops. All right, so next up is number 3. And in number 3, we have our liquid water. So we have our liquid water. It started at 0 degrees Celsius, and it rises until it gets to 100 degrees Celsius. So we are heating liquid water. So again, the temperature changes. And because the temperature changes, we're going to be able to use Q equals MC delta T. Any questions about why we can use that Q equals MC delta T, our Q equals MCAT on number 1 and number 3, but we cannot use it on number 2? Okay. So next up, we're going to look at number 4. So number 4 is another phase change. And here, again, we don't have any change in temperature. That means we can't use Q equals MC delta T. So here we are vaporizing or boiling our water. We are converting it from liquid to gas, and there is no temperature change. Oops. All right, so no change in temperature. Because there's no change in temperature, we're going to use enthalpy again. This time, we're going to use delta H vape, also known as delta H of vaporization. So again, whenever you have no temperature change, you cannot use Q equals MCAT because the delta T will go to 0 and then the whole thing will become 0. So anytime you have a phase change, you will always be using this enthalpy right here, the delta H. If you are boiling or vaporizing, it's going to be delta H of vaporization. If you are melting, it's going to be delta H of fusion. So one of the ways that I always remembered that fusion meant melting when I was a student is back in the day, smoothies were really popular, and there was a place called Juice Fusion, and they would take all the berries and all the frozen stuff and they would blend it up in their blenders and out would come a liquid. So to me, when I think of Juice Fusion, I thought of all these frozen fruits that ended up going from the solid state to the liquid state. But one way or the other, you want to remember that fusion is for melting. And then I think most of us will be able to remember vaporization is for the boiling. But any questions on anything so far? Okay. So if you had to take a guess for number 5 right here, and I did color code them, so that's a big hint, what are we going to use for number 5? Are we going to use Q equals MCAT, or are we going to use our delta H?
Q equals MCAT.
Excellent. Q equals MCAT. Because here what we're doing is we are heating up our gas. So here we are heating gas. And since we are increasing our temperature, we are going to be able to use that Q equals MCAT, like so. All right. So any questions on how we're setting this up? Any questions about why some of them we get to use Q equals MCAT and some of them we have to use delta H values? All right. So what I want to do is go back here, and I'm just going to go ahead and label everything. So everywhere that I have in purple here, 1, 3, and 5, those were all Q equals MCAT. And everywhere I have labeled in black, that's 2 and 4, these are delta H values. So the first one is delta H of fusion, and or I guess I should say number 2 is delta H of fusion, and number 4, delta H of vaporization. All right, so I know that was a big setup to the problem, but any questions on anything so far? Oops, and I see. So good question. Is it possible to skip the phase change steps? And I guess the answer to that is not if you want the correct answer. So what you're going to see is that for the Q equals MCAT for 1, 3, and 5, we're going to have different C values. So you do really have to break this up into 5 steps. So really they're not if you want the correct answer, there's no way to skip the steps. You could do it in a different, you could calculate them in whatever order you want. And some people prefer to calculate 1, 3, and 5 and then go back and do 2 and 4, but you do have to eventually do all of them. Yeah. All right, other questions so far? All right, so let's go ahead and start calculating this. I'm going to grab our heating curve so we can reference this. And I'm also going to grab our information here. And we are talking about 2.50 grams of ice. And I think it was just 5 degrees Celsius. All right, so here is our problem in a nutshell. And we're going to go through and we're going to start with number 1. Again, it is possible to do it in a different order, but you do eventually have to get all of these steps done. So I'm going to start with number 1. So number 1 is our Q equals MCAT. All right, all of these steps are going to have the same amount of ice. So in this case, we have 2.50 grams of ice, and that will be consistent throughout the whole problem. Next up, we have to think about the fact that we are dealing with ice. So here are our C values. So we have water, we have ice, and we have water vapor. So always make sure you're grabbing the right value. So for ice, we're right here, 2.09 joules divided by grams times degrees Celsius, like so. So any questions on why I use this value right here and not the value on the right or the left of it?
Just curious, though. Do we have to memorize the specific heat for ice and water vapor, or is the first one fine?
So all I need you to memorize is the one for water. Anything else I'll give you.
Okay, cool. Thank you.
Mm-hmm. All right, so next we need to do our change in temperature. So what is the change in temperature for step 1 only? How much did the temperature change? Excellent. So I'm seeing 5s. Excellent. So people have a tendency to want to do the entire temperature change and say it's 115 degrees. But we're only looking right now at this step right here. So in this step right here, it has only changed by 5 degrees Celsius. Any questions on why our change in temperature will only be 5 degrees? All right, so we got 5 degrees Celsius here. So go ahead and take a moment and calculate out your Q. Once you get a Q value, feel free to put that into the chat box. All right, so I'm seeing some 26.1. And the temperature is included, but go ahead and give us a few sig figs for now and we'll deal with the sig figs at the end. But yes, it is true. In general, we have to consider all the numbers. All right, so sounds like we're getting a lot of 26.1 for our answers. Any questions on that, or anybody getting different values? Sorry, just moving some windows around here. All right. Okay, so before we go on, I want to convert this into kilojoules, and that's because we're going to need it later. So if I wanted to convert 26.1 joules into kilojoules, I'm just going to do that through dimensional analysis. Those of you who are thinking, hey, I don't need dimensional analysis, I can do it in my head, you're more than welcome to. But I'm going to go ahead and say for every 1,000 joules, there is 1 kilojoule. And then I'm going to call this 0.0261 kilojoules like so. Any questions on how I did that conversion between joules and kilojoules? There we go. All right. So next up, let's do number 2. And number 2 is going to be a little different because it is a phase change. So way back in number 2, we said here we're dealing with melting. So we have to deal with that delta H of fusion. And here our delta H of fusion is 6.02 kilojoules per mole. And again, this is our delta H of fusion. So this is for melting. Okay, so here we have a slightly different situation, and that is because we have moles. So last time, back up in our Q equals MCAT, we were dealing with grams. Oops, not what I meant. But now we're dealing with moles, so we're going to do a conversion. We're going to convert that 2.50 into moles.
Hi, Professor.
Hey.
There's something wrong, and the bottom half doesn't seem to be moving.
The bottom half, my screen's not moving.
Of your shared screen?
Okay, let me, I'm going to stop the share and let me start it one more time. And let's see. So, is everything moving okay now?
Yeah, looks good.
Okay, thank you very much. Yeah, if you guys ever see anything weird, please let me know. All right, so we were doing 2.50 grams, and this is grams of ice, which is also H2O. And now we're going to convert them into moles using our molar mass. So 18.02 grams of H2O for every 1 mole H2O. And that's just coming off our periodic table. For every two hydrogens and 1 water, we get 18.02. And now if I take that 2.50 divided by 18.02, it looks like I'm getting point, and I'm going to use a few sig figs, and we'll deal with our sig figs at the end. So I'm going to say 0.13, I'll go ahead and say 87 moles of our water. So any questions on how I did the grams to moles conversion? Okay. So now I'm going to start off with those moles and say 0.1387 moles of our water. Now I'm going to use this delta H value as a conversion factor. So this one right here becomes my conversion factor, and I'm going to say 6.02 kilojoules for every 1 mole of H2O. So any questions on how I took this delta H value and I turned it into our conversion factor? Okay. So let's go ahead and calculate this. We have our moles. Now I'm going to multiply it by 6.02. And it looks like we have 0.835 in kilojoules like so. So any questions on how we found our kilojoules here for step 2? And here are kilojoules from step 1. All right. So next up, what I'm going to ask you to do is try step 3, 4, and 5. So we need to know how much energy is required for step 3, step 4, and step 5, and then we'll be adding everything together. First off, anybody need this screen a little longer for our step 2 or our step 1? Okay, so I see yes for the screen, and then I also see a question, will it always be in kilojoules? So you can do it in either joules or kilojoules, but you're going to have to do a conversion, either taking the kilojoules into joules or taking the joules into kilojoules. So in other words, they'll all have to be in the same unit. I find kilojoules to be the easiest one because it's going to be a lot of joules at the end, but unless the problem asks for kilojoules, it's your choice whether to go into joules or kilojoules. But either way, there will be a conversion. And how are we doing? Anyone still need the screen that's up right now? Okay. All right, so go ahead and try 3, 4, and 5 here. So you have the values down at the bottom, and then 3, 4, and 5, you have the chart at the top where 3 and 5 are your Q equals MCAT, and 4 is going to be your delta H of vaporization. And I see your question, Michael, and yes, you are correct. So the change in temperature for number 3 is 100 because you're going from 0 to 100. Yes. So while you guys are working, I'm going to play around with a function I haven't used before. It's called breakout room. So it allows you to be in a small group with just a couple of other students. That way, I'm hoping you might feel more comfortable sharing with each other and asking each other questions. So I'm going to give this a try. So in just a moment, you're going to find yourself in a breakout room with a couple of your classmates. And I'm going to try my best to group you with somebody who you sit near in lecture. So hopefully you'll recognize them. If this doesn't work and you guys hate it, we won't do it again. But I just wanted to give it a shot.
Professor?
Mm-hmm.
For the vaporization, going from grams to kilojoules, could we just do a straight conversion instead of like, you know how we did for number 2, we just broke it up, we got the answer for mole, and then we did another conversion?
Mm-hmm. If you want to just go straight across, you're welcome to. Yep.
Thank you.
Oh, you're welcome. Okay, so I tried to put everybody with people that they knew, so I apologize if I'm putting you with a group of people you don't know yet, but I'm going to go ahead and send you to your room. So once you get there, if you don't mind just introducing yourself briefly and then comparing answers, seeing how everybody is doing. Once you're in your rooms, you can always still type to me. There's a place where you can flag me if you want some help, and then I'm going to come visit you guys in your rooms. So you're about to go to the breakout rooms. All right, so make sure you're joining your breakout rooms. All right, so Jury and Brianna, go ahead and join that breakout room. Jury and Brianna, are you having any trouble getting into those breakout rooms? Hi, everybody. How's everything going here?
Going pretty well.
Excellent. And I know that Nino and Nico know each other. Did everybody else get a chance to say hello? We have Juan and Julian as well. Okay, so feel free to unmute and talk freely with each other. Once you get some answers, feel free to compare, or you can compare at any point along the way. So I'm going to go ahead and visit a few other rooms, but oh, okay. So I hear Nico's at work, but he's listening. So Nico, feel free to type. That's okay, Nico. Go ahead and feel free to type with your roommates here, your breakout roommates. And if you need me, there should be a link on there to flag me down, and I'm going to go ahead and jump into some of the other breakout rooms. Hi, Athena. It seems like you ended up in a breakout room by yourself. Oops. Hi, Athena. It seems like you ended up in a breakout room by yourself. I'm sorry.
I'm having trouble with my laptop.
Okay.
I don't know what happened with the Wi-Fi, but I'm on my phone.
Okay.
And it's like really, I haven't got it with my phone, but there were people and they left, but I'm still like trying to figure out. It's okay. I was gonna wait till the end.
Oh, okay. No worries. If you want to leave, there should be a button at the bottom that says "Leave Breakout Room," and then you can go back to the main room.
Oh, just bring me back.
That'll bring you back to the main room. Yeah. Okay.
Okay.
Okay. I'm gonna jump into a few other rooms.
Oh, gotcha. Oh, okay. Thank you. I found it.
Okay. How's everybody? Oh, how's everybody doing here?
Doing good. So just want to make sure that the value for M stays the same through all the parts. It's always 2.5.
It is always 2.5, although be careful because on 2 and 4, where you're changing phase, then you have to use the moles instead of the grams, but it is still that same value, yes. So what I mean is once you've taken that 2.5 and you've turned it into moles, that 0.1387, you'll then use the mole value for 2 and 4.
Gotcha.
Excellent. All right, and did everybody get a chance to meet each other? It looks like we have Chris and Tasso, Andrew, and Christian here.
Yeah. Yep.
All right.
Yeah, we're all here.
All right, excellent. So go ahead and keep working. Feel free to unmute and chat with each other, or you can type into the chat box to each other. And if you need me, there should be a button there to flag me down. I'm going to check on a few other people, and then I will see you in a little bit.
So, are you still there?
Oh, yes. Did you have questions?
Oh, yeah. Just about the homework that's due today. Will that be open until the end of class today, so 9:45?
Yes, I'm hoping to get it by the end of the day, but with everything going on with the online class, if you need a little bit more time, just let me know.
Okay, great. Thank you.
Oh, you're welcome. And how's everybody doing here? Looks like we're in the main chat room here. Any questions on anything? Oops, I have my chat box somewhere. Okay. All right, so I'm going to jump into a few of these breakout rooms and check on people. How's everybody doing here? All right, so it sounds like Angie says it's doing okay. I hope you haven't had a chance to meet each other. Feel free to unmute and talk. I wasn't sure who was friends with who, so I just kind of grouped a whole bunch of you together. I think you all sit near that near the doors there in class. So we got Maria, Angie, Nicole, Kayla, Sarah, Kimberly, and Jury here. So feel free to unmute and chat or type to each other. How's the problem going?
It's going good.
Okay.
We agreed on answers for like 3, 4, and 5. We're just discussing the final answer.
Okay.
And like sig figs.
Okay, that sounds great. All right, so if you guys do finish up, feel free to click the leave breakout room at the bottom, and you'll come back to the main room. And if you need me, there should be a button to flag me down there to ask a question. All right, so I'm going to jump into another room, and I will see you all soon.
Okay, thank you.
Oh, you're welcome. Hi, Eddie and Jervin. How are you two doing?
I think we're doing well.
Excellent. And you had a chance to meet each other?
Yep.
All right, excellent. All right, so whenever you guys finish, feel free to click the leave breakout room, and then you will jump back into the main room, and I'll be bouncing back and forth, but if you need me, there should be a link to flag me down.
Are we on break, or?
Well, everybody's supposed to be working on this problem. How are you doing with the problem? Are you all done?
Oh, yeah, we're pretty much done.
Okay, then feel free to click that leave breakout room and then come back.
Oh, one question.
Oh, yes.
So because there was like a 5 degrees Celsius at the very beginning, the final answer will be 1 sig fig?
Let's talk about sig figs together because it gets a little complicated because we're going to have that addition. But
okay.
Yeah, let's talk about the sig figs together.
Okay.
Okay.
All right. Thank you.
You're welcome. Hi everyone, sorry it took me a little bit to get over here, but how are you all doing? Did you all get a chance to meet each other? It looks like we have Andrew and Mike and Aljon. Yes, no, maybe? And Abel's here as well? Okay, perfect. All right, so we got about 1 more minute and then I'm gonna bring everybody back to the main room. All right, so I think we have everybody back. All right, so I think we've got everybody back. All right, so what did you guys think of the breakout rooms? Any thoughts? Do you like them, dislike them?
It was good.
Okay, excellent. So maybe we'll do those in the future when we're working on problems. I think I kind of overshot our break time a little bit, so let's go ahead and take a break and let's come back at all right, so let's go ahead and get started again, and let's see. We have a question coming in. When getting MCAT and Delta are always supposed to be... Okay, I see a great question. We had a similar one earlier, whether we need to be in kilojoules or in joules. So unless the problem asks for a specific unit, it's up to you whether you want to use kilojoules or joules. Just make sure everything's in the same unit. But let's go ahead and keep working on this problem. So before we split up, we did 1 and 2 together, and then in your groups you did number 3. So you had Q equals, and then the mass is the same throughout the problem. So, oops, what was it? 2.50. 2.50 grams. And now we're doing liquid water. So this is 4.184 joules divided by grams times degrees Celsius. And I saw earlier correctly that it was 100 degrees Celsius. So any questions here or any questions on why we're using 100 degrees Celsius as our change in temperature? All right. So what did y'all get for your Q? First in joules and then in kilojoules for number 3. Anyone want to bravely type in their answer for number 3? All right, so I see 1046 in joules. Sounds like several of you are getting that. So now what was that in kilojoules?
1.046.
Yes. All right, so any questions on anything for number 3 about why we use Q equals MCAT or anything else here? All right, so next up you did delta H of vaporization, and delta H of vaporization was 40.7 kilojoules per mole. And we had already found our moles above. We said that we had 0.1387 moles. And now I'm multiplying it by that delta H of vaporization that says there is 40.7 kilojoules in every 1 mole. So what did you get for your kilojoules in number 4?
5.645.
All right, so I'm hearing 5.645. How about the rest of you? Did you get something similar, different? All right, so it sounds like everybody's getting similar answers here. All right, and then finally we're going to heat up our steam. So Q equals MCAT again. And we have that same mass of 2.50 grams. But now we're in steam, so we need to look up our C value for steam. And it's right over here, so 2.01 joules divided by grams times degrees Celsius. Times the change in temperature. And, oh, I see a question from earlier. Is 5.65 not okay? That is fine. We're going to look at our sig figs in just a minute. And it looks like we went up by 10 degrees Celsius here. So any questions? And again, we haven't talked about sig figs yet. We're going to do that in just a moment. But any questions here about how we set up number 5? All right, so what did y'all get for your Q value first in joules and then in kilojoules for number 5?
50.25 joules.
All right, 50.25 joules. And did everybody get something similar? It sounds like Tasso got something similar and Maria as well. Excellent. And then what did y'all get in kilojoules? All right, so I'm hearing 0.05025. Oops, straighten out my 0 there. All right, everybody get something similar? Anybody have questions on how we got our values here? All right. All right, so next up I want to do 2 things. First is check our sig figs, and then we're going to add everything up. So I'm going to go up to the very first one. So our very first one, it looks like we're at 1 significant figure. So I'm going to put a line right here over that 2. So that'll be our last sig fig when we add this up. And I'm going to copy this and bring it down. So this was from number 1. Next up is number 2. And number 2, it looks like we had 3 significant figures, so that's what we have written as our answer. Oops. Like so. So all I'm doing is bringing down our previous answers, and as I do it, I'm checking their sig figs. So this was 3 sig figs, just like it was supposed to be. All right, next up, number 3. So I'm going to consider this 100 to be exact, and the reason is that it was from freezing to boiling. So we assume it freezes at an exact 0, and we assume that it boils at an exact 100. So I'm going to call this 3 sig figs. Like so. Any questions about why I called that 100 exact? Or anything else so far? All right, next up will be number 4. And here's our number 4, and it looks like we had 3 sig figs coming from that delta H of vaporization. So this will be 3 sig figs as well. And finally, we're going to get to number 5. And number 5, that 10 degrees, it was from an exact 100, and then it went to 110 degrees Celsius. It's tough to tell. This is an ambiguous number. I'm going to call this, we're going to have to make a judgment call on this one. I'm going to go ahead and call that 2 sig figs. But in this one right here, we had 110 minus 100. If this one is exact, and this is a whole number, I'm going to go with 10 being 2 sig figs. So we didn't really have a good value right here. I really should have had 10.0, or I'm sorry, 110.0. So I'm just going to estimate it as 2 sig figs. So I apologize, that's not a really solid answer on those sig figs. I should have done better with that 110 there. But, oops. There we go. So I'm going to say that 10 is 2 significant figures, and that'll leave us with 2 sig figs here. All right. So I know the sig figs weren't as secure as we usually have them, but any questions on how we got these values or what we're talking about with the sig figs here? Okay, so let's go ahead and add these up. Come on. All right, so it looks like 0.0261 plus 0.835 plus 1.046 plus 5.645 plus 0.05025. All right, so when you guys added this up, did everybody get something close to that 7.60? Okay, excellent. So the number in its entirety, I'm going to say 7.60235 kilojoules. Then I'm going to look at my sig figs. This is 2 digits after the decimal, 3 after the decimal, 2 after the decimal, 2 after the decimal, and 3 after the decimal. So I'm going to cut this off after 2 after the decimal and call this 7.60 kilojoules. So this is a tough problem. I wouldn't focus too much on the sig figs. I would focus more on understanding it and kind of being able to do it. Any questions on anything that we've done here? Yes, 7.61 would be just fine. Let's see. Yes, so Angie's asking, what if we were doing something similar, but the substance was other than water? Then I would definitely give you the melting and boiling temperatures. So the only melting and boiling I would expect you to know is water. All right, so other questions on this one? Okay, so I know this was a big problem, but remember, this is not covered on our exam coming up on Wednesday. This is going to be for exam 3. So, all right. Questions on anything so far, though? All right. All right, so next up, we're going to move on to bomb calorimetry. So it's similar to what we talked about before break, but it's slightly different. So let's talk about the similarities first. So with calorimetry, we said we're going to do a chemical reaction, and it's going to be contained inside of an insulated container, and there's going to be water in there to absorb the heat, and we're going to measure the water so that we know how much heat was released from our chemical reaction. So all of that is the same. The difference here is that we have a little bomb inside, and we call it a bomb. What is really going on here is this is a container, and inside of there we have an explosive. So just like a bomb that you would think of, but it is contained. It is not going to break that container. We designed those containers specifically so that it does not break that container. And we even have little ignition wires in here, just like if you were watching TV and you would imagine there's a bomb, there are some wires that need to be cut. All of that is inside of here. So what's in this silver gray container is a bomb. It is an organic substance that can explode if it is ignited with wires, which is exactly what's happening. Now the rest of it, again, is going to be very similar. You have water outside of your bomb. When this bomb explodes, we assume all of its heat's going to go into that water that is surrounding the bomb. And we are going to measure the temperature through this thermometer here. And when we measure that temperature, we're going to be able to figure out how much heat was given off by the bomb. Because this is a fully enclosed calorimeter, usually these are large, these are pretty heavy. It's tough to swirl them. If you had gotten a chance to do the calorimetry experiment in lab, you would have had your coffee cup calorimeter and you would have swirled it around. But these devices are large, and again, you can't just take it and move it around to swirl it. So we usually do have motorized stirrers, which is what you see here on the left. All right, but questions on anything so far with that bomb calorimeter? All right, so just a little bit of the background theory here. Is there pressure in the chamber? Is it unpressurized? There is going to be a lot of pressure in this container right here. So normally there's actually a little bit of, not a screw, but a spring in there, and it will allow for a little bit of release of the pressure, but it is a high pressure container and it's meant to contain that high pressure. So here's a little bit of the background. So we say that heat at constant volume, in answer to the question, not the water. The water is not pressurized. It's the little tiny bomb inside of there that's pressurized. All right, so here this is heat at constant volume. And we assume this bomb does have constant volume. Nothing is really getting increasing or decreasing in volume. And so we say it's equal to delta E. And by convention, whenever we do bomb calorimetry, we like to talk about delta E instead of Q. So they are the same so long as our container has constant volume. And so by convention, we have Q of reaction. It is calculated for a reaction based on how much of your reactant there is. So when we're calculating Q, we're saying how much heat for whatever you put in there. So if you put in, say, 5 grams, you have twice as much heat generated as if you put in 2.5. So again, Q depends on how much stuff is in there, but delta E does not. By convention, when we do delta E, we take the Q of a reaction and we divide it by the moles. So when we talk about delta E, it is always heat per mole. So this is what we'll be doing for the calorimeter. So I'm going to make a note here that this is sort of background. And when I say background, what I mean is I'm not going to be testing you on it ever, but I still think it is just good to know where everything's coming from. So here's our problem, and it is bomb calorimetry. And again, this is not coming on Wednesday's exam. This is for exam 3. But should bomb calorimetry come on a quiz or exam, I'm not going to try to trick you. You're going to see the word bomb right there in the question. So when you're looking at one of these calorimetry problems, and somewhere in there it will say calorimeter or calorimetry, so again, not trying to trick you, that word bomb will be right there too. All right, so it says when 1.010 grams of sucrose undergoes a combustion in that bomb calorimeter, the temperature rises from 24.92 to 28.33. And now it says find delta E of reaction. And again, whenever you're in bombs, we're using delta E of reaction for the combustion of sucrose in kilojoules per mole. And the heat capacity of the calorimeter is 4.90 kilojoules per degree Celsius. All right, so when you're doing bomb calorimetry, the C is always about the calorimeter. It's never about the substance. And we have a slightly different formula. So rather than Q equals MCAT, you're using Q equals CAT. And this is for bomb calorimetry only. So that's why you need to look out for this word bomb that will be in your problem. So here, the Q for the calorimeter, the heat gained by the calorimeter, is going to be C, which is the heat capacity of the calorimeter, times the change in time. So let's start off with that. So again, because we have a bomb calorimeter, that is why we're going to use the Q equals cat. And this is Q for the calorimeter, and this is C for the calorimeter. All right, so we want to know how much heat will be gained by the calorimeter. So we start off with our C value, 4.90. And it has units of kilojoules divided by degrees Celsius. So sometimes when students are doing this, they say, well, I can't remember whether I need to add grams or not. If you look at the units right here, you'll notice there's no grams in there. So because there's no grams in there, that's a good indication that you do not need the grams. And that is true. Anytime you're in bomb calorimetry, you're not going to put grams into here. So next up we have change in temperature, and we're always doing T final minus T initial. So final temperature, 28.33. Initial temperature right over here, 24.92. Okay. Any questions about what we're doing so far or why we're not using Q equals MCAT, why we're not putting the mass in here? All right, so let's go ahead and calculate this. So I'm going to do the parentheses first. So 28.33 minus 24.92. And it looks like when I do that, I get 3.41 degrees Celsius. And we're going to multiply that by 4.90. All right, so multiplying that by 4.90. And it looks like the Q for our calorimeter, the amount of heat absorbed by the calorimeter. I'm going to go ahead and keep all my sig figs for now, 16.709, but in the end, that is a 3 sig fig answer, and that's in kilojoules. All right, so questions on anything that I did here or any of my calculations?
So in the problem, they give us 1.01 grams of sucrose. That's just unnecessary information.
It's going to be coming up next, so let's take a look at what we're doing. Oops, sorry about that. All right, we've just used this right here, and this will be step number 1. Where we're going to use it is we're going to use it right down here in what I'm going to call step number 3. But we do get to use it. But that's what's confusing for a lot of people because you're given these grams, and we've done so much Q equals MCAT, everybody wants to throw those in. But you don't get to use the grams until this last step when we'll be converting them into moles. But very good question. All right, so we just found the Q of the calorimeter. Now we need to find the Q of the reaction. So the Q of the reaction is the same value but with opposite sign. So it's going to be negative 16.709 kilojoules like so. What we said way back when is that our system and our surroundings have the same amount of energy. However, one is giving it away and one is absorbing it. In our case, we have a bomb exploding. So this is exothermic. It's given off its energy and the calorimeter is taking it in. So when we said Q of the calorimeter is a positive 16.709, that positive is because it took in that energy, but our reaction itself gave it out. So for your final answer for bomb calorimetry, it should always be negative. Every bomb includes exothermic material, so bombs explode outwards, they do not take energy in. So again, for bomb calorimetry, you should always have a negative for your final answer. Any questions on what we did there for step 2 when we changed the signs from positive to negative? All right, so in our step 3, this is where the grams are going to come in. We are going to calculate our change in energy for the reaction, which will be Q reaction over moles. So this is the change in energy, and again, we like to do it in kilojoules per mole. So we'll do Q of reaction divided by moles. So for our calculation, we already know Q of reaction. It's negative 16.709 kilojoules like so. But what we don't know yet are the moles, and that's where those grams come in. Clean this up here. All right, so we've got to figure out how many moles these are, and that's a simple grams to moles conversion. So I'm going to say 1.010 grams. And next we're going to use the molar mass of our sucrose. All right, so we have 12 carbons, and those are 12.01. And it looks like we have 22 of our hydrogens, 1.008, plus 11 of our oxygen, which are each 16. So it looks like I'm coming up with a molar mass of 342. For those of you calculating on your own, are you getting similar values? Yes? Okay, excellent. All right, so into here I'm going to put 342.296. Okay, so I did that molar mass calculation quickly. Any questions on how I came up with that value? These are just carbon, hydrogen, oxygen from the periodic table. Okay. Oops. Put that calculator away too soon. All right, so 1.010 divided by our molar mass. And it looks like I'm going to get 0.00, and I'm going to say 295. And these are the moles of our sucrose. And let me clean that up a bit. All right, for those of you calculating along, did you get something similar to 0.00295? Excellent. All right, so finally we're going to plug that in, 0.00295, and actually it looks like I should have had one more sig fig here. Put a 1 on there. All right. So now let's calculate out our delta E of reaction. So negative 16.709 divided by our moles. And it looks like our change in energy to 3 significant figures, negative, say 5.66 times 10 to the 3rd kilojoules per mole. All right, so questions about anything that we've done here? All right, so this is our final answer right here. This is our delta E. So remember, for your final answer for any bomb calorimetry problem, it's got to be negative. These are all exothermic reactions. You have a bomb, it's going to explode, it's going to give off heat and energy. All right. But questions about anything that we did here for the bomb calorimetry? Okay. There's lots of excitement there in the background, but I don't think, sadly, I don't think it's for chemistry. All right. All right. So, any questions on anything here?
Where do you find the 4.9 kilojoules per Celsius again?
So that's going to be our C value right here, and that's coming from our problem. So that is right over here. So the
okay, I didn't see that.
yep, and this heat capacity and bomb calorimetry has to be given to you.
Okay, thank you.
All right, so other questions so far? All right, and that is the end of this chapter. So again, where our exam that you're going to see on Wednesday ends is right up here. So what we did today is not on the exam, although I will warn you, this right here was a review problem. So we did do similar ones before break. So the real new problem came with the heating curves. So heating curves and calorimetry are not going to be on the exam on Wednesday. All right. So questions on anything else here? All right.